Hello and welcome, I'm the Toastering Kid. Today I want to talk about a problem that will use a lot of data and it will be pretty interesting, but first we need to go over some basic physics, and if you're familiar with it, you should have seen a problem like this at some point in your life. A roller coaster is at the top of a hill at a height of h, and when it goes down the hill, at the bottom, what will be its velocity? And this problem is always used to illustrate potential energy and kinetic energy. At the top of the hill, a roller coaster will have potential energy, and at the bottom, it will have only kinetic energy. Roller coasters are such a good illustration of this because potential energy can be kind of hard to visualize at some times, because roller coasters, from that point at the top of the hill onwards, all it is being powered by is that initial potential energy. It just coasts the rest of the way, only powered by potential energy, and it's being converted into and out of kinetic energy as it traverses its layout. And to solve this problem, you would say that potential energy equals kinetic energy because energy is conserved, and set them equal to each other, cancel out the mass, and then solve for V, and you get that V equals the square root of 2gh, where h is that height, and g equals the gravitational constant. It is 9.81 meters per second squared. That is the acceleration every object on Earth experiences in freefall. So say if h equals 100 meters, at the bottom, its velocity will be 44.3 meters per second. But say you want to flip this problem. Is this really true? This is the question I want to ask in this video. Is what we're taught in schools, how close is it to reality? And the way to do this is we rearrange that v equals the square root of 2gh equation, and we set that equal to g. So we can plug in v and h and see what g value we get. So let's do this for a real roller coaster. Let's pick a random roller coaster, and it looks like we got lost gravity at Walibi Holland. So let's have a picture of it for the backdrop here. And the height of it is 105 feet and the speed is 54.1 miles per hour. And to make things simple, we will be converting these into metric units, so then 105 feet will be equal to 32 meters and 54.1 miles per hour is equal to 24.2 meters per second. And then if we plug these values in, we get that the g value is 9.15 meters per second squared. So that's not 9.81, is it? But this is just one roller coaster. Let's look at all the roller coasters. Let's look at over 1,000 roller coasters. Yes, I went through Roller Coaster Database and got all of the heights and speeds listed for roller coasters that had them both on the website. And here they are plotted all on one graph. And this could be pretty fun to look at. Up here you see Formula Wassa, the world's fastest roller coaster. Down here is Dododonpa. And these are roller coasters that are pretty short for those speeds. And over here we have King of the Ka and Top Thrill Dragster, and down here we have the Dita roller coasters. So let's just throw up all the labels to make it more interesting. See if you can pick out a few. And if you can't, let's zoom in a bit. And, that's enough of that. It's a bit too cluttered. There's just so many roller coasters here. But all we're interested in is the data. And analyzing it, we see that it does follow a trend. To some degree, every roller coaster is scattered everywhere. Every roller coaster is its own special snowflake. But it does follow that trend that the velocity increases with height at a decreasing rate. And there's even a little question mark here as if it is asking us to solve this issue. And so let's see how well it matches up with the equation we found earlier, v equals the square root of 2gh. And we see that it does match up pretty decently with the data. But it looks like more data points fall below the trend line than far above it. So what is the best fit equation for this data? So if we rearrange v equals the square root of 2gh to v squared over 2 equals g times h, then if we plot v squared over 2 and h on the same chart, we should get a straight line with a slope of g. And so here we have them all on the chart, and the best fit equation using regression, we can find this mathematically, and that is v squared over 2 equals 8.58 times h. So that means that g equals 8.58 meters per second squared, not 9.81 meters per second squared. But I'll tell you what's going on here. It's that on average, a roller coaster drops less than it is tall. It will have a drop height less than the height on average. You see, I labeled it like that in the original equation, and maybe a few of you caught on there. So to get a better value for v, you'd use the height d here, not h. the drop height is a listed stat on roller coaster database. So if we use those instead of height, we get a much tighter graph, which makes sense. Some roller coasters will drop more than they are tall, but on average, a roller coaster will drop less than it is tall because it always stops a few feet above the ground, or even more. So then if we use this set of data to find a value for g, we should get much closer. So doing the same thing we did before, the best fit equation using regression, we did that the speed equals the square root of 2 times 9.44 meters per second squared times h. So we're still not quite there, but quite a bit closer. But that's pretty fascinating that, we're so close anyway. And if you plot the two equations, the theoretical and what we just got, on the same graph, we see that they are so close they might as well be the same. But let's try to do this a different method. Let's do like we did for lost gravity and solve for g for every single roller coaster. And so here are those g values for all of those rides on the same histogram, and the average value for all of those coasters is 9.78 meters per second squared. We pretty much got it. We are right there. Pretty amazing, right? Except not really, because the average value is skewed quite a lot by these really high g values that are mostly for launch coasters that will just launch right over their drops with tons of kinetic energy, which throws off the data. So if we get rid of these outliers, plus or minus 1 standard deviation away from the mean, we get our new average g value of 9.42 meters per second squared. So we're pretty much right back where we started. So you can see how regression is a pretty good method because it naturally avoids these outliers. We still have g values all over the place because every roller coaster is its own special snowflake. They all have different little things that make them inaccurate. So let's look at roller coasters just from one manufacturer to try to decrease this variance a bit. Let's look at B&M because they're a big maker of roller coasters and they're pretty standard across the board. So here we are, here's the chart, and let's throw the labels on there, see if you can pick out a few. And I hope you had your fun, so let's just throw the labels away, convert them right back into the right units, and get our regression equation, and that is g equals 9.08 meters per second squared. So we're even further away with just the B&M roller coasters, even if the graph tightened up quite a bit. You can still see that we are pretty close to the theoretical equation for these B&M roller coasters, and actually if we plot all of the g values on the imperial unit chart, we see that, there's not a whole lot of difference in between these different g values, because the differences in speed will be proportional to the square root of g instead of g itself. So say for example, the drop is 200 feet, and if you find the speed values for each of these g values, then just plus or minus a few miles per hour apart. But in terms of energy lost, because it's proportional to g or v squared, then for B&M roller coasters we're losing up to 7.5% of this energy, and for the drop speed relationship we're losing 3.8% energy over that first drop. And I know some of you might be thinking, what about that initial speed roller coasters go over on the lift hill? They don't have only potential energy, they do have some kinetic energy because they are moving on the chain lift. And yeah, that's true. And if we accounted for that, we get even slightly lower g over g values. So it is at least 3.8% energy lost. So where is all this energy going? It's not really lost, it is being converted into other sources. And some of the ways that energy is being converted is through aerodynamic resistance, rolling resistance, and deflection of the structure. All of these, to some degree, will slow down the roller coaster and lead to lower kinetic energy at the bottom of the hill. So it isn't really true that we can say potential energy equals kinetic energy because it is being converted into all these other sources. It's more like potential energy equals kinetic energy plus a little more because energy is always conserved. But still, at 7.5% for B&M roller coasters, it's just over one drop. How can we have such a high value? Well, I hope to explain that a little bit. And, through rolling resistance, that comes from the fact that wheels are not wound. And it's true because if you look at this picture of my car tire, you see that at the bottom it is compressed to counteract the weight of the car. The tire has some pressure in it, and that pressure needs to be applied over an area to equal the weight of the car. And that leads to the wheel not being wound, and that will create a moment about the wheel which slows down the car when it's moving. And same applies to coasters because they are polyurethane wheels, and those will compress a bit because they're not made of steel. And the force of rolling resistance is equal to a constant times the weight. And remember that the weight of a roller coaster will be much higher at the bottom of a drop because of the extra g-forces applied. And that constant also increases with weight and velocity, so you can see how rolling resistance can contribute a lot to slowing down the roller coaster at the bottom of a drop. Another is aerodynamic resistance, and aerodynamic resistance comes from how roller coasters are moving through dense air, and that will exert a force on the roller coaster that is equal to the density of air times the drag coefficient times its frontal area times the velocity squared. And that's important that velocity is squared, which leads to pretty high forces of drag. So let's calculate this for a B&M roller coaster Fury 325, and we have to estimate a few things like the area, let's say 4.5 meters squared. The coefficient of drag is really hard to estimate because you really need to know the total shape and material of everything. But let's just say it's 1 because you might be somewhere in the ballpark with 1. Let's just keep it at that. And the velocity, we'll say, is 60 meters per second, which is equal to 80 miles per hour. And remember, the top speed of Fury 325 is 95 miles per hour. It's pretty fast. So we're going to calculate the force when it's not quite at the bottom of the drop. And plugging in all of our numbers, we get that the force of drag is equal to 3,572 newtons. And to estimate the effect of this on slowing down the roller coaster, we need to estimate the mass of the train. And let's just say an empty coaster train is equal to 5 times the weight of the riders. That's another rough estimate, but all we're trying to prove is that, drag exists and we can't ignore it. And, for this estimate, we get that the acceleration, or the deceleration rather, due to drag is 0.27 meters per second squared. So you can see how that takes up a pretty big chunk of that 9.81. And lastly, we have deflection of structure, and that comes from the fact that to force the train along its route, the track exerts forces on the train, and the train will also exert forces on the track, and that will cause the track to compress and the whole structure to compress. And that compression acts like a spring, which stores a lot of energy. So here we have steel vengeance going over the first drop, and you can see that the structure and the track deflects a lot as it goes down and exerts a force, and that stores a ton of energy. So all these effects, if you're designing a roller coaster or even just trying to calculate the top speed, can't be ignored. And then that's where we have lower G values than 9.81. So that's why in our original problem, it usually comes with a caveat, ignore friction. But say it doesn't come with that caveat, just plug in 9.4 for G, and you can argue that you will get a closer answer to reality. So hope you learned something. I've been the Toastering Kid. I found this pretty interesting. See you next time.